Right now, as you watch this, your coffee is getting cold. The ice in your drink is melting. Your phone battery is draining. And in this exact moment, you are witnessing the same force that will one day kill every star, extinguish every galaxy, and reduce the entire universe to an ocean of darkness so complete that nothing, absolutely nothing, will ever happen again. This isn't philosophy, this is thermodynamics, and it has already begun. The second law of thermodynamics states that entropy, the measure of disorder in a system, always increases. Always. Without exception. Every process in the universe, from the nuclear fusion in stars to the firing of neurons in your brain, creates more disorder than order, more chaos than structure, more heat death than life. And unlike every other law of physics, this one has a direction. Time's arrow points in only one direction, toward maximum entropy, toward the heat death of everything. In 1998, two teams of astronomers made a discovery that would fundamentally alter our understanding of the universe's fate. Led by Saul Perlmutter at Lawrence Berkeley National Laboratory and Brian Schmidt at the Australian National University, they were studying distant supernovae, exploding stars that serve as cosmic measuring sticks. What they found defied every prediction. The universe wasn't just expanding, it was accelerating. Something was pushing the fabric of space itself apart, faster and faster, overcoming even gravity's pull. They called it dark energy, and it comprises roughly 68% of everything that exists. In 2011, they received the Nobel Prize in Physics. But their discovery also sealed the universe's doom. Because of dark energy, galaxies are racing away from each other at ever-increasing speeds. Eventually, they will recede faster than light itself can travel between them. The universe will become not just dark, but fundamentally disconnected. Islands of matter separated by gulfs of space so vast that no signal, no light, no information can ever cross them again. Each galaxy will die alone, in absolute isolation, with no possibility of rescue or contact. This is called the Big Rip scenario, though the more likely outcome is even stranger. The Big Freeze, where the universe doesn't tear apart but simply runs down, like a clock that no one will ever wind again. Let me show you what this looks like on a timeline that compresses all of cosmic future into something your mind can grasp. Imagine that the current age of the universe, 13.8 billion years, is compressed into a single second, one heartbeat. In this scale, we are living in the first microsecond after the Big Bang. The universe is young, hot, dense with stars and galaxies and light. Now let's watch what happens next. In the next second, another 13.8 billion years, the last massive stars will have already died. Star formation will slow dramatically as galaxies exhaust their reserves of hydrogen gas. The universe will grow noticeably dimmer. In 10 seconds, 138 billion years from now, the smallest, longest-lived red dwarf stars will begin to flicker out. These stars, barely massive enough to sustain fusion, can burn for trillions of years. But even they cannot escape entropy's grip. By 100 seconds on our compressed timeline, 1.3 trillion years in real time, the last star in the universe will die. Not with a supernova, not with any drama at all. It will simply cool, darken, and become a black dwarf, a lump of carbon and oxygen floating in the void, radiating no light, generating no heat, doing nothing at all. The stelliferous era, the age of stars, will be over, and it will have lasted less than 1/1,000,000,000% of the universe's total lifespan. But the universe will not be empty. Not yet. It will be filled with the corpses of stars, white dwarfs, neutron stars, and black holes. These objects will orbit each other in the darkness, occasionally colliding, releasing brief flashes of gravitational waves that no one will ever detect. Galaxies will still exist as structures, though they will be invisible, composed entirely of stellar remnants and planets that have long since frozen to temperatures barely above absolute zero. This is the degenerate era, and it will last for an incomprehensibly long time. During this era, something remarkable will happen, though it will take longer than your mind can truly comprehend. Black holes, those gravitational monsters that devour everything, will begin to evaporate. In 1974, Stephen Hawking, working at the University of Cambridge, discovered that black holes are not entirely black. Due to quantum effects at the event horizon, they emit radiation. Incredibly faint radiation. A black hole with the mass of our Sun would take 10 to the power of 67 years to evaporate completely. That's a 1 followed by 67 zeros. A number so large that if you wrote 1 zero per second, you would need more than 2 trillion years just to write it down. But stellar mass black holes are nothing compared to the supermassive black holes at the centers of galaxies. The black hole at the center of our Milky Way, Sagittarius A star, has a mass of roughly 4 million suns. It will take 10 to the power of 99 years to evaporate. The largest black holes we've observed, with masses exceeding 10 billion suns, will persist for 10 to the power of 100 years or more. These timescales are so vast that the entire history of stars, trillions upon trillions of years, becomes a brief flash, a moment of cosmic youth before the real eternity begins. And here is where the story becomes truly strange. As black holes evaporate, they will be the last sources of energy in the universe. The Hawking radiation they emit will be the only thing happening. Particles will occasionally pop into existence near the event horizon, one falling in, one escaping, slowly draining the black hole's mass. This process will accelerate as the black hole shrinks, until finally, in a burst of gamma rays lasting less than a second, the black hole will vanish completely. And then, there will be one fewer source of energy in the universe. One fewer thing happening. Eventually, every black hole will evaporate. Every last one. The supermassive monsters at galactic centers, the stellar remnants scattered through space, even the tiny black holes that might have formed in the early universe, all of them will decay into radiation, and that radiation will spread out, redshift, cool, and become indistinguishable from the background temperature of space itself. This marks the end of the black hole era, and the beginning of something that physicists call, with appropriate bleakness, the dark era. In the dark era, the universe will consist almost entirely of photons, particles of light, and leptons, the family of particles that includes electrons. These particles will be spread so thinly through space that the average distance between them will be measured in light years, perhaps light centuries. The temperature of the universe will be a tiny fraction of a degree above absolute zero. Nothing will orbit anything else because gravitational interactions require proximity, and proximity will no longer exist. The universe will be a cold, dark, expanding void where nothing happens, nothing changes, and nothing ever will again. But even this is not the end, because there is one more process that might occur, though it operates on timescales that make black hole evaporation look instantaneous. Proton decay. The protons that make up atomic nuclei, the building blocks of all matter, may not be stable. Grand unified theories in physics predict that protons should eventually decay into lighter particles. The current experimental lower limit on proton lifetime is 10 to the power of 34 years. But if protons do decay, it will likely take 10 to the power of 40 years or longer. Imagine that timeline, 10 to the power of 40 years. That's 10,000 trillion years. In this unimaginable future, the last remnants of matter, the black dwarfs, the neutron stars, the frozen planets, will slowly dissolve. Atom by atom, proton by proton, they will decay into radiation and scatter into the void. The universe will transition from a state of mostly nothing to a state of absolutely nothing but photons and leptons, separated by distances so vast that they might as well not exist at all. And then comes the final state, the true heat death, maximum entropy, a universe in perfect thermodynamic equilibrium, where every region of space has exactly the same temperature, the same density, the same nothingness. No gradients, no differences, no possibility of energy flowing from one place to another because there are no places in any meaningful sense. Just an infinite, eternal, unchanging sameness. The long thermodynamic silence. In this state, time loses all meaning. Because time, as we experience it, is defined by change, by cause and effect, by the flow of energy from hot to cold, from order to disorder. But in a universe at maximum entropy, nothing changes. Ever. 1 trillion years passes, and the universe looks exactly the same. 1 trillion years passes, and still nothing happens. You could wait 10 to the power of 100 years, a Google, and the universe would be identical to how it was a Google years earlier. Time becomes a dimension without direction, without content, without purpose. This is not a distant abstraction. This is the actual, physical fate of our universe, according to our best understanding of physics. Every calculation points to this conclusion. Every observation confirms it. The universe is not cyclical. It will not collapse and rebound. It will not be saved by some unknown force or phenomenon. It will simply expand, cool, and die. And we are living in the brief, brilliant flash before the eternal darkness. Now, I understand what you might be thinking. This sounds like nihilism, like cosmic despair, like everything we do, everything we build, everything we love is ultimately meaningless because it will all end in heat death anyway. And in a sense, that's true. The universe does not care about human civilization. It does not care about art or love or the accumulated knowledge of billions of minds. Entropy will erase it all with the same indifference that it erases stars. But here's what makes this story fascinating rather than depressing. We figured it out. We, a species of primates on a small planet orbiting an ordinary star in an unremarkable galaxy, used mathematics and observation and reason to predict the fate of the entire universe. We looked at the cooling coffee and the melting ice and extrapolated forward 10 to the power of 100 years. We understood entropy not as a vague concept, but as a precise, quantifiable law that governs everything from chemical reactions to the death of galaxies. The second law of thermodynamics was first formulated in the 1850s by Rudolf Clausius, a German physicist working at the University of Zurich. He was studying steam engines, practical industrial machines, and discovered a principle that would turn out to be far more profound than anyone imagined. In any closed system, he realized, the total entropy can never decrease. Heat flows from hot to cold, never the reverse, unless you add energy from outside. And the universe, by definition, has no outside. It is the ultimate closed system. In 1865, Clausius wrote a paper that ended with two stark statements. The energy of the universe is constant. The entropy of the universe tends to a maximum. These two sentences contain the entire fate of everything. Energy cannot be created or destroyed, only transformed. And every transformation increases disorder. The universe started in a state of incredibly low entropy, hot, dense, uniform, and has been sliding toward maximum entropy ever since. The Big Bang was not an explosion into space. It was an explosion of space. And that explosion set entropy's clock ticking. For decades, physicists debated what maximum entropy would look like. Would the universe collapse back on itself in a big crunch, resetting the clock? In the 1920s, Alexander Friedmann and Georges Lemaitre showed that Einstein's equations of general relativity allowed for an expanding universe. But the expansion could slow down and reverse if there was enough matter. For most of the 20th century, cosmologists argued about whether we lived in an open universe that would expand forever or a closed universe that would eventually contract. Then came 1998 and the discovery of dark energy. The debate was over. The universe is not just open, it's accelerating. The expansion will never stop, never slow down. Galaxies will recede beyond our cosmic horizon, disappearing from view not because they've been destroyed, but because space itself is stretching faster than light can cross it. In 100 billion years, any civilization in our galaxy will look out at the night sky and see nothing. No other galaxies, no cosmic microwave background, no evidence that the universe is anything other than the Milky Way surrounded by infinite darkness. They will have no way to discover the Big Bang, no way to measure the expansion of space, no way to know that they live in a universe with a history and a future. Unless they find our records, our observations, our calculations, our understanding, they will be cosmologically blind. We are living in a unique window of time when the universe is old enough to be understood, but young enough to be observed. In the deep future, that window will close forever. But let's zoom in. Because the heat death of the universe isn't just a cosmic abstraction, it's happening right now, at every scale, in every process, including inside your own body. Entropy isn't waiting for the far future. It's operating in this moment, in the cells of your brain, in the atoms of the air you breathe, in the quantum foam of space-time itself. To understand how the universe dies, we need to understand how entropy works at every level of reality, from the smallest particles to the largest structures in existence. Start with your body. Right now, your cells are performing roughly 37 trillion chemical reactions per second. Each reaction converts high-energy molecules like ATP, adenosine triphosphate, into lower-energy products, releasing heat in the process. This heat radiates from your skin into the surrounding air, increasing the entropy of your environment. You are, quite literally, an entropy-generating machine. Every thought you think, every movement you make, every heartbeat that keeps you alive is paid for with an increase in universal disorder. Your body maintains its internal order, its low entropy state, only by consuming external sources of low entropy. Food. The chemical bonds in a sandwich contain concentrated energy, low entropy, compared to the heat and waste products your body will produce after digesting it. But where did that low entropy come from? From plants, which captured photons from the sun through photosynthesis. And where did the sun get its low entropy? From the gravitational collapse of a hydrogen cloud 4.6 billion years ago, which converted gravitational potential energy into the nuclear fusion that powers our star. Trace it back far enough, and all the low entropy in the universe, all the order, all the structure, all the possibility of anything happening at all, comes from the initial conditions of the Big Bang. The universe started in an incredibly low entropy state, and it has been paying down that entropy debt ever since. Every star that forms, every planet that coalesces, every life form that evolves is temporarily decreasing local entropy by increasing entropy somewhere else. The second law is never violated. It cannot be violated. The universe is running a one-way transaction, and the account is slowly draining to zero. Now let's examine what happens at the quantum level, because this is where entropy becomes truly strange. In quantum mechanics, particles don't have definite positions or velocities until they're measured. They exist in superpositions, multiple states simultaneously, described by a mathematical object called a wave function. When you measure a particle, the wave function collapses into a single definite state. And here's the crucial part. This collapse is irreversible. It increases entropy. In 1957, Hugh Everett, a graduate student at Princeton University, proposed a radical solution to this problem. What if the wave function never collapses? What if every possible outcome of every quantum measurement actually occurs, but in different branches of reality? This is the many worlds interpretation of quantum mechanics, and while it sounds like science fiction, it's taken seriously by many physicists because it eliminates the need for wave function collapse and preserves the reversibility of quantum mechanics. But here's the catch. Even in the many worlds interpretation, entropy increases. Not because wave functions collapse, but because observers become entangled with the systems they measure. You measure a particle's spin, and your brain state becomes correlated with that spin. The information about which branch you're in becomes encoded in your neurons, in the positions of atoms, in patterns that spread outward through space like ripples in a pond. This spreading of information, This decoherence is entropy increase by another name. The universe doesn't need wave function collapse to obey the second law. Entropy wins either way. Consider a specific example: the decay of a radioactive atom. Uranium-238 has a half-life of 4.5 billion years. That means if you have a sample of uranium-238, half of it will decay into thorium-234 over that time period. But here's what's remarkable. You cannot predict when any individual atom will decay. Quantum mechanics gives you only probabilities. The atom exists in a superposition of decayed and not decayed until something, a detector, a passing particle, the cosmic microwave background, interacts with it and forces it into one state or the other. When the atom decays, it releases an alpha particle, 2 protons and 2 neutrons bound together, with a specific kinetic energy. That alpha particle collides with other atoms, transferring its energy, creating heat, increasing entropy. The information about the atom's initial state becomes scrambled across billions of particles. This is entropy at the quantum level, the irreversible spreading of information from concentrated, ordered states into diffuse, disordered states. Now scale up. Consider a star. Our sun converts roughly 600 million tons of hydrogen into helium every single second through nuclear fusion. Each fusion reaction releases energy in the form of gamma-ray photons. These photons don't escape the sun immediately. They scatter off electrons and nuclei, bouncing around inside the sun's core for roughly 100,000 years before finally reaching the surface and radiating into space as visible light. By the time a photon reaches Earth, it has been redshifted, scattered, and degraded from a high-energy gamma ray into thousands of lower-energy, visible, and infrared photons. Entropy has increased. But here's what makes stars fascinating from an entropy perspective. They are temporary decreases in local entropy, powered by an even larger increase in entropy elsewhere. When a cloud of hydrogen gas collapses under its own gravity to form a star, the gas heats up. Gravitational potential energy converts into kinetic energy, the random motion of particles. The cloud becomes more disordered at the microscopic level, even as it becomes more ordered at the macroscopic level, forming a spherical star instead of a diffuse cloud. The net entropy of the system increases because the star radiates heat into space, and that radiated heat increases the entropy of the universe far more than the star's formation decreased it. This is the pattern everywhere: local order purchased with universal disorder. A snowflake forms, creating a beautiful crystalline structure, but only because the water vapor in the cloud released heat as it froze, warming the surrounding air. A human civilization builds cities and computers and spacecraft, creating islands of incredible order, but only by burning fossil fuels and nuclear reactions and sunlight, dumping waste heat into the environment. Every act of creation is simultaneously an act of destruction. Every increase in order here requires a larger increase in disorder there. Let's examine a specific mechanism of entropy increase that will dominate the far future: Hawking radiation. When Stephen Hawking discovered that black holes emit radiation, he solved one of the deepest puzzles in theoretical physics: the black hole information paradox. If you throw a book into a black hole, where does the information in that book go? Classical general relativity says it's lost forever, hidden behind the event horizon. But quantum mechanics says information cannot be destroyed. It can be scrambled, encrypted, spread out, but never truly lost. Hawking's calculations showed that black holes emit thermal radiation, random, featureless heat, with a temperature inversely proportional to their mass. A black hole with the mass of the Sun has a temperature of roughly 60 billionths of a degree above absolute zero. That's far colder than the cosmic microwave background, which currently sits at 2.7 degrees above absolute zero. So stellar mass black holes are actually absorbing more radiation from the universe than they emit. They're growing, not shrinking. But the cosmic microwave background is cooling as the universe expands. Its temperature drops in proportion to the scale factor of the universe. In roughly 100 billion years, the cosmic microwave background will cool below the Hawking temperature of stellar mass black holes. At that point, black holes will begin to evaporate. Slowly at first, unimaginably slowly, but inevitably. Here's what makes Hawking radiation so remarkable from an entropy perspective. It's the ultimate entropy-increasing process. A black hole is the most compact, ordered form of matter possible. All the information about what fell into it, the books, the stars, the planets, is encoded in quantum correlations at the event horizon, but it's maximally scrambled. When the black hole evaporates, that information is released as thermal radiation, spread across space in the most disordered form possible. The entropy of the universe increases by an enormous amount. In fact, black holes have the highest entropy of any object of a given size. The entropy of a black hole is proportional to the area of its event horizon, not its volume. This is called the Bekenstein-Hawking entropy, and it's given by a remarkably simple formula. S equals K times A divided by 4 times the Planck length squared, where K is Boltzmann's constant and A is the area of the event horizon. For a black hole with the mass of the Sun, this entropy is roughly 10 to the power of 54. That's a 1 followed by 54 zeros. More entropy than all the stars in the observable universe combined. When that black hole evaporates, all that entropy is released into the universe. And this will happen to every black hole eventually. The supermassive black hole at the center of the Andromeda Galaxy, with a mass of roughly 100 million suns, will evaporate in 10 to the power of 98 years. The largest black holes we've observed, like TUN 618 with a mass of 66 billion suns, will persist for 10 to the power of 106 years. But they will evaporate. Entropy guarantees it. Now let's consider what happens to ordinary matter over these timescales. Protons, the building blocks of atomic nuclei, are extraordinarily stable. We've never observed a proton decay. Experiments at facilities like the Super Kamiokande detector in Japan have placed a lower limit on proton lifetime of 10 to the power of 34 years. But many grand unified theories predict that protons should eventually decay, likely through a process mediated by hypothetical particles called X bosons. If protons decay, the timescale is probably around 10 to the power of 40 years. To put that in perspective, if you took every proton in your body, roughly 10 to the power of 28 of them, and waited 10 to the power of 40 years, only a tiny fraction would have decayed. But wait long enough, and they all will. Your body, the Earth, the Sun, every star and planet and asteroid, all of it will slowly dissolve into lighter particles. Positrons, neutrinos, photons. The universe will transition from a state containing matter to a state containing only radiation and leptons. But even this isn't the final state, because there's one more process that operates on even longer timescales: quantum tunneling. In quantum mechanics, particles can _8_quote__, through energy barriers that would be impossible to cross classically. The probability of tunneling decreases exponentially with the height and width of the barrier, but it's never exactly zero. Given enough time, truly staggering amounts of time, even the most improbable quantum events become inevitable. Consider a lump of iron floating in the void, a remnant of a long-dead star. Iron is the most stable nucleus. It has the highest binding energy per nucleon. It cannot undergo fusion or fission to release energy. Classically, it should remain iron forever. But quantum mechanically, there's a tiny probability that the nuclei in that iron will spontaneously rearrange themselves into a lower entropy configuration. Not lower energy, that's impossible, but lower entropy in the sense of being more spread out, more disordered. The timescale for this process is roughly 10 to the power of 1,500 years. That's not a typo. 10 to the power of 1,500. A number so large that if you tried to write it out, with 1 zero per atom in the observable universe, you would run out of atoms before you finished writing the number. This is the timescale on which quantum fluctuations can rearrange matter into arbitrary configurations. Given enough time, that lump of iron could spontaneously tunnel into a configuration that resembles a computer, or a brain, or anything else permitted by the laws of physics. This leads to one of the strangest predictions in all of cosmology: Boltzmann brains. In 1896, Ludwig Boltzmann, an Austrian physicist working at the University of Vienna, realized that if you wait long enough in a state of maximum entropy, random fluctuations will eventually create pockets of low entropy. A fluctuation that creates a single brain, complete with false memories of a life it never lived, is vastly more probable than a fluctuation that creates an entire universe with consistent physical laws and a long history. In the far future, after all the stars have died and all the black holes have evaporated, the universe will be in a state of near maximum entropy. But quote 9 is not the same as quote 10. There will still be tiny fluctuations, quantum jitters in the fabric of space-time. And given enough time, 10 to the power of 10 to the power of 100 years perhaps, these fluctuations will occasionally create structures. A few particles arranged in an ordered configuration. A brief flash of complexity in an ocean of nothingness. Most of these fluctuations will be tiny and meaningless, but very, very rarely, a fluctuation might create something complex enough to be called a quote 11. A structure capable of having experiences, of thinking thoughts, of observing the universe. This brain would exist for a fraction of a second before dissolving back into the void. It would have no past, no future, no context. Just a momentary spark of consciousness in an otherwise dead universe. Here's the disturbing part. If the universe lasts forever in a state of near maximum entropy, then the number of Boltzmann brains that will eventually fluctuate into existence is infinite. And the number of normal brains, brains like yours, created through the ordinary processes of stellar evolution and biological evolution, is finite. So in the long run, the vast majority of conscious experiences in the universe will be Boltzmann brains, not biological organisms. Most observers will be random fluctuations with false memories, not real beings with real histories. This is called the Boltzmann brain paradox, and it's one of the deepest problems in modern cosmology. If our theories predict that most observers are Boltzmann brains, and we are not Boltzmann brains, then our theories are probably wrong. Or we need to rethink what we mean by, quote, 13 in an infinite universe. Or we need to accept that the universe doesn't last forever in a state of near maximum entropy, that something else happens, something we don't yet understand. But based on our current understanding of physics, the most likely scenario is this. The universe will expand forever, cooling and diluting until it reaches a state of maximum entropy. At that point, nothing will happen for timescales that dwarf even the proton decay timescale. No stars, no black holes, no chemistry, no life. Just photons and leptons separated by distances measured in light centuries, all at the same temperature, all moving away from each other as space continues to expand. And then, very occasionally, a quantum fluctuation will create a brief pocket of low entropy. A few particles arranged in an ordered configuration. Most of these fluctuations will be meaningless, but every 10 to the power of 10 to the power of 100 years or so, a fluctuation might create something complex. A Boltzmann brain. A momentary observer in an otherwise empty universe. This is the ultimate fate of everything, according to our best current theories. Not a dramatic ending, but a slow fade into nothingness, punctuated by infinitely rare and infinitely brief sparks of complexity. The universe doesn't end with a bang or a whimper. It ends with silence, broken only by the occasional quantum whisper, too faint and too brief to mean anything at all. Now, you might be wondering, is there any way to escape this fate? Any loophole in the second law of thermodynamics? Any process that could reverse entropy and restart the universe? The short answer is no. The second law is not just a law, it's a statistical inevitability. It emerges from the fact that there are vastly more disordered states than ordered states, and random processes naturally explore all available states over time. Imagine a deck of cards. There's only one way to arrange the deck in perfect order, ace through king of each suit, in sequence. But there are roughly 10 to the power of 67 ways to arrange the deck in a random order. If you shuffle the deck repeatedly, you'll almost never return to the perfectly ordered state, simply because it's one configuration out of 10 to the power of 67 possibilities. The second law of thermodynamics is the same principle, applied to the universe. There are vastly more high-entropy states than low-entropy states, so the universe naturally evolves toward high entropy. But here's where it gets interesting. The second law is statistical, not absolute. It's possible, in principle, for entropy to decrease spontaneously. It's just incredibly unlikely. The probability of all the air molecules in your room spontaneously moving to one corner, leaving you in a vacuum, is not zero. It's roughly 10 to the power of -10 to the power of 23. That's a decimal point, followed by 10 to the power of 23 zeros, then a 1. A number so small that it might as well be zero for any practical purpose. But in an infinite universe, or a universe that lasts forever, even probabilities that small become certainties eventually. This is called the Poincaré recurrence theorem, named after Henri Poincaré, a French mathematician who proved in 1890 that any finite system will eventually return to a state arbitrarily close to its initial state, given enough time. The recurrence time for a system the size of the observable universe is roughly 10 to the power of 10 to the power of 120 years. That's a number so large that it makes the proton decay timescale look instantaneous. So in principle, if you wait 10 to the power of 10 to the power of 120 years, the universe might spontaneously return to a low-entropy state similar to the Big Bang. All the particles might randomly arrange themselves into a hot, dense, uniform state, and the whole process could start over. But there are two problems with this scenario. First, the recurrence time is so long that it's effectively infinite for any practical purpose. Second, and more importantly, the universe is not a finite system. It's expanding, and if dark energy continues to dominate, it will expand forever, creating new space faster than particles can recur. So Poincaré recurrence probably doesn't save us. The universe will not spontaneously reset. It will not cycle. It will simply expand, cool, and die, reaching a state of maximum entropy from which there is no return. This is the heat death, and it is as close to inevitable as anything in physics can be. But let's zoom out one more time, because there's a perspective that makes even the heat death seem less final. The universe we observe, the roughly 93 billion light-years of space containing 2 trillion galaxies, is not the entire universe. It's just the observable universe, the region from which light has had time to reach us since the Big Bang. Beyond our cosmic horizon, there's more space, more galaxies, more stars, possibly infinitely more. If the universe is infinite, then everything that can happen will happen, somewhere. There are regions of space where stars are still forming, where civilizations are still evolving, where the heat death is trillions of years away. And if the universe is truly infinite, then there are infinitely many such regions. The heat death is local, not universal. Our patch of space will die, but the universe as a whole, if it's infinite, will always contain regions of low entropy, regions where complexity and life are possible. This is called the eternal inflation scenario, and it's based on the theory that the Big Bang was not a single event, but an ongoing process. In certain regions of space, inflation, the exponential expansion that occurred in the first fraction of a second after the Big Bang, never stopped. These regions continue to inflate, creating new space, new pocket universes, new Big Bangs. Our observable universe is just one pocket in an infinite multiverse, and while our pocket will eventually die, the multiverse as a whole is eternal. But even this doesn't save us from entropy. Each pocket universe still obeys the second law. Each one still evolves toward maximum entropy. The multiverse as a whole might be eternal, but any given observer, any given civilization, any given consciousness will still experience the heat death of their local universe. The fact that other universes exist elsewhere doesn't change the fate of our own. And so we return to the fundamental truth. Entropy always increases. The universe is running down. The stars will die, the black holes will evaporate, the protons will decay, and eventually, nothing will remain but a cold, dark, expanding void where nothing happens and nothing ever will again. This is not speculation. This is not philosophy. This is physics, based on observations and calculations and the most fundamental laws we know. The heat death is coming. It has already begun. And there is nothing, absolutely nothing, that can stop it. But here's what nobody tells you about the heat death. It's already changing how we see ourselves, right now. Not in some distant future, but in this moment, as you process these words. Because once you understand that the universe is dying, truly understand it, not as abstract theory, but as physical inevitability, something shifts in your relationship to existence itself. The question is no longer, quote, 15, the question becomes, quote, 16. Let me show you what I mean by taking you inside the most sophisticated experiment ever designed to measure the universe's fate. In 2003, NASA launched the Wilkinson Microwave Anisotropy Probe, WMAP, to map the cosmic microwave background radiation with unprecedented precision. This radiation is the afterglow of the Big Bang, photons that have been traveling through space for 13.8 billion years, cooled by the expansion of the universe from trillions of degrees to just 2.7 degrees above absolute zero. The WMAP satellite spent 9 years measuring tiny temperature fluctuations in this radiation, variations of just a few millionths of a degree. These fluctuations are the seeds of all structure in the universe: galaxies, stars, planets, you. By analyzing their pattern, physicists could determine the universe's composition, age, and ultimate fate with extraordinary precision. The results were unambiguous. The universe is 73% dark energy, 23% dark matter, and only 4% ordinary matter. And that 73% dark energy is pushing space apart, accelerating the expansion, guaranteeing the heat death. But here's what makes this experiment philosophically profound. We built it knowing what it would tell us. We spent $800 million and 9 years of observation to confirm our own cosmic death sentence. Why? Because humans have this strange compulsion to understand, even when understanding brings no comfort. Especially when it brings no comfort. We would rather know the truth and face oblivion than live in ignorant hope. In 2013, the European Space Agency launched an even more sophisticated satellite, Planck. It measured the cosmic microwave background with such precision that it could detect temperature variations of 1 part in 100,000. The data confirmed WMAP's findings and added new details. The universe is not just expanding. It's expanding in a very specific way that rules out almost all alternative scenarios. No big crunch, no cyclic universe, no escape, just expansion, acceleration, and eventual heat death. The Planck satellite also measured something called the Scalar Spectral Index, a number that describes how the density fluctuations in the early universe varied with scale. The measured value is 0.965, with an uncertainty of just 0.004. This number tells us that the universe started in an incredibly low entropy state, far more ordered than random chance would predict. The Big Bang was not a maximum entropy explosion, it was a minimum entropy beginning, and everything since has been entropy's slow victory. Now let's talk about what this means for consciousness. Because if the universe is dying, and if consciousness is a physical process, neurons firing, synapses connecting, information processing, then consciousness itself is temporary. Not just your consciousness or mine, but consciousness as a phenomenon. The capacity for any system to be aware, to experience, to know that it exists. All of it will end. In 1994, David Chalmers, a philosopher at the Australian National University, published a paper that would define the modern study of consciousness. He distinguished between the easy problems of consciousness, explaining how the brain processes information, responds to stimuli, controls behavior, and the hard problem, explaining why there is subjective experience at all. Why does it feel like something to be you? Why is there an inner life, a first-person perspective, a sense of what it's like to see red, or taste coffee, or feel pain? The hard problem remains unsolved. We don't know why consciousness exists. But we do know that it's correlated with physical processes in the brain. Damage certain neurons, and you lose the ability to recognize faces. Damage others, and you lose the ability to form new memories. Consciousness appears to be what the brain does, not something separate from it. And if consciousness is physical, then it's subject to the same laws as everything else, including the second law of thermodynamics. Every thought you have increases entropy. The neurons in your brain consume glucose and oxygen, converting chemical energy into electrical signals and heat. That heat radiates into your surroundings, increasing the disorder of the universe. Your consciousness, your subjective experience of being alive, is paid for with entropy. And when the universe reaches maximum entropy, when there's no more energy to flow from hot to cold, no more gradients to power processes, consciousness will become impossible. Not just human consciousness, any consciousness, anywhere. This is what makes the heat death truly final. It's not just the death of matter or energy. Those are conserved, they can't be destroyed. It's the death of process, the death of change, the death of the possibility that anything could ever experience anything again. The universe will still exist in some sense. There will still be particles, still be space, still be time, but nothing will happen. No thoughts will be thought. No experiences will be experienced. The universe will be, but it will not know that it is. Unless, and this is where it gets interesting, consciousness is not what we think it is. In 2004, Max Tegmark, a physicist at MIT, proposed a radical idea. What if consciousness is not a special property of certain physical systems, but a fundamental aspect of reality itself? What if the universe is, in some sense, conscious, not in the way humans are conscious, but in a more basic, mathematical sense? What if subjective experience is woven into the fabric of space-time, and what we call consciousness is just a particularly complex pattern of this universal awareness? This is called panpsychism, and while it sounds like mysticism, it's taken seriously by some physicists and philosophers because it offers a potential solution to the hard problem. If consciousness is fundamental, then you don't need to explain how it emerges from unconscious matter. It was there all along. The brain doesn't create consciousness. It focuses it, shapes it, gives it structure and content. But the raw capacity for experience is built into reality itself. If panpsychism is true, then the heat death doesn't end consciousness. It just reduces it to its most basic form. The universe at maximum entropy would still be conscious, in some minimal sense. Not thinking thoughts or having experiences in any way we'd recognize, but still possessing that fundamental quality of what it's like to be. A kind of cosmic dreamless sleep, lasting forever. But here's the problem. We have no evidence for panpsychism. It's an elegant idea, but it doesn't make testable predictions. It doesn't explain anything that our current theories don't already explain. And Occam's razor, the principle that we should prefer simpler explanations, suggests we shouldn't multiply entities beyond necessity. If we can explain consciousness as an emergent property of complex information processing, we don't need to invoke a fundamental consciousness field. So the most likely scenario remains: consciousness is what brains do, and when there are no more brains, no more complex structures capable of processing information, there will be no more consciousness. The universe will die not just physically, but experientially. The lights will go out, and there will be no one left to notice. Now let's examine what happens to information itself in the far future. Because information, like energy, is subject to thermodynamic laws. In 1948, Claude Shannon, working at Bell Labs, published a paper that founded the field of information theory. He showed that information can be quantified, measured in units called bits, and that there's a fundamental relationship between information and entropy. In fact, they're the same thing, viewed from different perspectives. Entropy is missing information, the number of possible microstates consistent with a given macrostate. Information is negative entropy, the reduction in uncertainty when you learn something new. This means that as the universe evolves toward maximum entropy, it's also evolving toward maximum information loss. Every process that increases entropy destroys information about the past. When you burn a book, the information in the book isn't destroyed. It's scrambled into the pattern of smoke and ash and radiated heat. In principle, if you knew the exact position and velocity of every particle, you could reconstruct the book. But in practice, that information is lost forever, mixed into the thermal noise of the environment. In the far future, after all the stars have died and all the black holes have evaporated, the universe will be in a state of maximum entropy and minimum information. There will be no records of what came before. No fossils, no ruins, no cosmic microwave background to study. Just a uniform sea of particles at the same temperature, with no way to distinguish one region from another. The entire history of the universe, the Big Bang, the formation of galaxies, the evolution of life, everything that ever happened, will be erased, scrambled beyond recovery. But here's where it gets strange. Quantum mechanics suggests that information is never truly destroyed. This is called unitarity, and it's one of the fundamental principles of quantum theory. The wave function of the universe evolves according to the Schrödinger equation, which is reversible. If you know the wave function at one time, you can calculate it at any other time, forward or backward. Information is conserved. This creates a paradox when you combine quantum mechanics with black holes. Hawking's original calculations suggested that black holes destroy information. They absorb matter with specific quantum states and emit featureless thermal radiation. But if information is conserved, where does it go? This is the black hole information paradox, and it's been one of the central problems in theoretical physics for 50 years. In the 1990s, Leonard Susskind at Stanford and Gerard 't Hooft at Utrecht University proposed a solution, the holographic principle. They suggested that all the information about what falls into a black hole is encoded on its event horizon, like a hologram. The three-dimensional interior of the black hole is completely described by two-dimensional information on its surface. When the black hole evaporates, that information is released in the Hawking radiation, encoded in subtle correlations between the emitted particles. If the holographic principle is correct, then information is conserved even in black hole evaporation. But here's the catch. The information is scrambled so thoroughly that it's effectively impossible to recover. You would need to collect every single photon emitted by the black hole over its entire evaporation time, 10 to the power of 100 years for the largest black holes, and perform calculations that would require more computational resources than exist in the observable universe. The information is there, but it's lost for all practical purposes. This is the ultimate fate of information in the universe, not destroyed, but scrambled beyond recovery. The history of everything, every thought ever thought, every word ever spoken, every moment ever experienced, will be encoded in the quantum correlations of particles separated by light centuries, at temperatures a fraction of a degree above absolute zero. Preserved in principle, but lost in practice. A cosmic library burned to ash, with every book still technically present in the pattern of smoke, but impossible to read. Now let's talk about time itself, because the heat death doesn't just end processes, it ends time as we know it. Time, as we experience it, is defined by change, by cause and effect, by the flow of energy from past to future, from order to disorder. But at maximum entropy, there is no change, no cause and effect, no flow. Time becomes a dimension without direction, without meaning, without content. In 1967, Stephen Hawking and Roger Penrose proved a series of theorems about the nature of time in general relativity. They showed that under very general conditions, space-time must contain singularities. points where the curvature becomes infinite and the laws of physics break down. The Big Bang is one such singularity. Black holes contain others. These singularities mark the boundaries of time itself, places where time begins or ends. But the heat death is not a singularity. It's not a point where the laws of physics break down. It's a state where the laws of physics continue to operate perfectly, but nothing happens. Time continues to exist as a dimension of space-time, but it becomes empty of events. You could wait 1 trillion years, and the universe would look exactly the same. Wait another trillion, and still nothing would have changed. Time becomes a stage with no actors, a clock with no hands, a dimension that exists but means nothing. This raises a profound question. If nothing changes, does time still exist? Is time a fundamental feature of reality, or is it an emergent property of change? If the universe reaches a state where nothing ever happens again, has time ended, or does it continue forever in a state of eternal sameness? Different physicists give different answers. Some argue that time is fundamental, built into the structure of space-time itself, and continues to exist even when nothing changes. Others argue that time is emergent, arising from the thermodynamic arrow, the direction of increasing entropy, and ceases to be meaningful at maximum entropy. Still others suggest that time might be an illusion, a feature of our subjective experience rather than an objective property of reality. But regardless of which interpretation is correct, the practical result is the same. At maximum entropy, time loses its significance. The universe enters a state that is, for all practical purposes, timeless. Not because time has ended, but because nothing happens to mark its passage. An eternity of nothingness, where a second and 1 trillion years are indistinguishable because both contain exactly 0 events. Now let's examine the one process that might offer a way out. Vacuum decay. The vacuum of space is not truly empty. It's filled with quantum fields that permeate all of reality. These fields have a ground state, a lowest energy configuration, that we call the vacuum. But what if the vacuum we observe is not the true ground state? What if it's a false vacuum, a metastable state that could decay to a lower energy true vacuum? In 1980, Sidney Coleman and Frank DeLucia, working at Harvard, calculated what would happen if the vacuum decayed. A bubble of true vacuum would nucleate somewhere in space, expanding at the speed of light. Inside the bubble, the laws of physics would be different. Particles would have different masses, forces would have different strengths, atoms might not be stable. The bubble wall would destroy everything it touched, converting matter and energy into the new vacuum state. If vacuum decay occurs, it would be the ultimate catastrophe. Not just the end of life or consciousness, but the end of chemistry, of atoms, of the possibility of any structure at all. The universe would be sterilized, reduced to a featureless soup of particles in their new ground state. And because the bubble expands at light speed, there would be no warning, no way to see it coming, no way to escape. One moment you exist, the next moment the bubble wall passes through you, and you cease to exist in any meaningful sense. But here's the strange part. Vacuum decay might be preferable to heat death. Because vacuum decay would happen quickly, over thousands or millions of years, not trillions. And it would create a new universe with new physics, possibly new forms of complexity, new possibilities for structure and life. The heat death, by contrast, is slow, inevitable, and final. No reset, no new beginning, just an endless fade into nothingness. Current measurements suggest that our vacuum is probably stable, or at least metastable, with a lifetime far longer than the current age of the universe. In 2012, after the discovery of the Higgs boson at CERN, physicists calculated the stability of the vacuum based on the measured Higgs mass of 125 giga-electron-volts. The result was unsettling. The vacuum appears to be metastable, sitting in a local minimum, rather than the absolute minimum of energy. But the decay rate is so slow that the expected lifetime is at least 10 to the power of 100 years, far longer than the heat death timescale. So, vacuum decay probably won't save us from the heat death. The universe will expand, cool, and die long before the vacuum has a chance to decay. We're stuck with entropy's slow victory. But let's consider one more possibility: the role of intelligence. Because humans are not passive observers of the universe's fate, we're active participants, capable of understanding the laws of physics and potentially manipulating them. Could a sufficiently advanced civilization find a way to survive the heat death? To extract energy from the vacuum itself? To create new universes and escape into them? In 1979, Freeman Dyson, working at the Institute for Advanced Study, published a paper titled Time Without End: Physics and Biology in an Open Universe. He asked whether life could survive indefinitely in an ever-expanding universe. His conclusion was cautiously optimistic. If a civilization could adapt to ever lower temperatures and ever slower metabolisms, it might be possible to continue thinking, experiencing, and existing for an infinite subjective time, even as the universe cooled toward absolute zero. Dyson's scenario requires several assumptions: that protons don't decay, that intelligence can be implemented in substrates other than biological neurons, and that a civilization can harvest energy from the rotation of black holes or other exotic sources. But even if all these assumptions hold, the civilization would face diminishing returns. Each thought would take longer and longer to process. Each experience would be stretched over greater and greater timescales. Subjective time might be infinite, but objective time would still march toward heat death. And if protons do decay, as most grand unified theories predict, then even Dyson's scenario fails. There would be no matter left to build computers, or bodies, or any substrate for consciousness. Just radiation and leptons, spreading ever thinner through space, unable to form structures or process information. Intelligence would become impossible, not just impractical. So we return, again and again, to the same conclusion. The heat death is inevitable. The universe is dying. Entropy is winning. And there is no escape, no loophole, no way out. The laws of physics are clear, and they point in only one direction: toward maximum entropy, toward the end of all process, toward the long thermodynamic silence. But here's what makes this story bearable. We know. We understand. We've traced the arc of cosmic history, from the Big Bang to the heat death, from minimum entropy to maximum entropy, from the first moment of time to the last. We've calculated the timescales, measured the constants, predicted the future with mathematical precision. We are the universe becoming aware of itself, understanding its own fate, staring into the abyss with clear eyes and steady minds. And in that understanding, there is something profound. Not comfort exactly, not hope in any conventional sense, but a kind of cosmic perspective that makes our brief existence more precious, not less. We are patterns of low entropy in a universe sliding toward disorder. We are temporary islands of complexity in an ocean of simplicity. We are the universe's way of experiencing itself before the lights go out. The heat death is coming, but it is not here yet. And in the time we have, whether that's decades or centuries or millions of years, we can think, create, love, understand. We can build civilizations and write symphonies and solve equations. We can look up at the stars and know what they are, how they formed, how they will die. We can be conscious, aware, alive. That is not nothing. That is everything. But let me tell you what happens when you truly internalize this knowledge. Not just intellectually, but viscerally. When you understand, in your bones, that the universe is dying and taking everything with it. Something unexpected occurs. Something that defies the nihilism you might expect. Because the heat death, paradoxically, makes everything more meaningful, not less. Consider this. Right now, at this exact moment, you are participating in the most improbable event in cosmic history. Not your birth, though that's improbable enough. Not human civilization, though that's a statistical miracle. but this: the fact that the universe is currently in a state where complexity is possible at all, where stars can form, where planets can coalesce, where chemistry can create life, where neurons can fire in patterns complex enough to understand entropy itself. This window of possibility is astonishingly narrow. The universe is 13.8 billion years old. In another 100 trillion years, the last star will die. That means we're living in the first 0.01% of cosmic history. The brief flash when the universe is awake, aware, capable of knowing itself. After that comes an eternity of darkness so long that the entire age of stars becomes a rounding error. A cosmic eye blink before the endless night. Let me show you exactly how narrow this window is by examining the most extreme environments where complexity can still exist. In 2016, astronomers using the Hubble Space Telescope discovered a galaxy called GNZ11, located 13.4 billion light-years away. We're seeing it as it was just 400 million years after the Big Bang, when the universe was only 3% of its current age. This galaxy was forming stars at a rate 20 times faster than the Milky Way does today, frantically converting hydrogen into heavier elements before the cosmic expansion could dilute its gas reserves. GN11 represents the beginning of the complexity window, the moment when the universe had cooled enough for gravity to pull matter together, but was still dense enough for vigorous star formation. Before this, the universe was too hot and uniform. After the heat death, it will be too cold and diffuse. We exist in the Goldilocks zone of cosmic history, and that zone is vanishingly brief. Now let's examine the other end of the window. In 2012, a team led by Laughlin and Adams at the University of Michigan published detailed calculations of stellar evolution in the far future. They showed that the smallest red dwarf stars, those with masses around 0.08 times the Sun, can sustain fusion for up to 10 trillion years. These stars burn so slowly, so efficiently, that they'll outlive every other stellar object by factors of thousands. But even these miserly stars have limits. As they fuse hydrogen into helium, their cores gradually fill with helium ash. Eventually, the hydrogen fuel runs out. The fusion stops. The star contracts, heats briefly, then cools forever, becoming a black dwarf, a lump of degenerate matter radiating no light, generating no energy, doing nothing at all. The last red dwarf will die around the year 10 trillion CE, give or take a few hundred billion years. After that, the universe enters what astronomers call the degenerate era. No more stars, no more fusion, no more light. Just the corpses, white dwarfs, neutron stars, black holes, and planets that have long since frozen to temperatures barely distinguishable from the cosmic background. This era will last far longer than the Stelliferous era, perhaps 10 to the power of 40 years, dominated by the slow decay of protons and the even slower evaporation of black holes. But here's what makes this timeline philosophically devastating. Consciousness almost certainly cannot survive the degenerate era. Not because the laws of physics forbid it, but because consciousness requires energy gradients. It requires the flow of energy from hot to cold, from order to disorder. It requires stars, or at least stellar remnants warm enough to power computation. Once the last black holes evaporate, once the last protons decay, there will be no energy sources left, no gradients, no possibility of any process, including thought. This means that consciousness, the universe's ability to know itself, is even more temporary than matter. Matter persists in some form until proton decay. But consciousness probably ends much earlier, when the last stars die and the universe becomes too cold to support complex information processing. We're not just living in the first 0.01% of cosmic history. We're living in perhaps the only 0.01% when the universe can be aware of itself. Let me make this concrete with a thought experiment. Imagine you could compress the entire timeline of the universe, from the Big Bang to the heat death, into a single human lifetime of 80 years. In this scale, the Big Bang happens at the moment of your birth. The first stars form when you're about 3 days old. The sun forms when you're roughly 56 years old. Human civilization emerges in the last half second before your 80th birthday, and you die, representing the heat death, at age 80. Now here's the crucial question. When does consciousness exist in this timeline? When is the universe aware? The answer is shocking. Only in the last few years of your life. Before age 56, there are no planets, no chemistry, no possibility of life. After age 80, there's nothing but cold darkness. Consciousness exists only in that narrow window between late middle age and death. And human-level consciousness? That exists only in the final half second. We are living at the peak of cosmic complexity. This moment, right now, is as good as it gets. The universe will never be more alive, more aware, more capable of understanding itself than it is today. From here, it's all downhill. Slow at first, then faster, then inevitable. The stars will die, the galaxies will fade, the black holes will evaporate, and consciousness will wink out, leaving behind a universe that continues to exist, but has no way to know that it does. Now, I know what you're thinking. This sounds like the ultimate argument for nihilism. If everything ends, if consciousness is temporary, if the universe will eventually reach a state where nothing matters because nothing can matter, then why does anything matter now? Why build civilizations? Why create art? Why love, learn, strive, hope? Why do anything at all if entropy will erase it eventually? This is the question that haunted Ludwig Boltzmann himself. In 1896, after formulating the statistical interpretation of entropy, Boltzmann fell into a deep depression. He understood, perhaps more clearly than anyone before him, that the second law of thermodynamics was not just a physical principle, but an existential verdict. The universe was dying, and there was nothing anyone could do about it. In 1906, while on vacation in Italy, Boltzmann hanged himself. He was 62 years old. But here's what Boltzmann missed, what took another century of physics to understand. The heat death doesn't make life meaningless. It makes life precious. Because meaning is not something the universe gives us. It's something we create, here and now, in defiance of entropy. Every act of creation, every painting, every equation, every moment of love, is a local decrease in entropy, purchased with a larger increase elsewhere. We are entropy's rebellion against itself. We are the universe's way of saying, quote, 21 to the heat death. Let me show you what I mean by examining the most ambitious attempt ever made to preserve human knowledge against cosmic timescales. In 1977, NASA launched Voyager 1 and Voyager 2, twin spacecraft designed to explore the outer solar system. Each carried a golden record, a 12-inch gold-plated copper disc containing sounds and images selected to portray the diversity of life and culture on Earth. Music from Bach and Beethoven, greetings in 55 languages, images of human anatomy, architecture, landscapes. A message in a bottle, thrown into the cosmic ocean. The Voyager spacecraft are now in interstellar space, traveling at roughly 17 kilometers per second. In 40,000 years, Voyager 1 will pass within 1.6 light-years of the star Gliese 445. In 300,000 years, it will reach the Oort cloud of another star system. And barring a collision with something, the spacecraft and their golden records will survive for billions of years, long after the sun has died, long after Earth has been consumed or ejected from the solar system. But here's the thing. The golden records are not really for aliens. The probability that any extraterrestrial civilization will find them is essentially zero. Space is too vast, the spacecraft too small, the galaxy too empty. The golden records are for us. They're a statement that we existed, that we created, that we mattered, even if no one ever finds them. They're humanity's way of saying, quote, 22 to a universe that will eventually forget. And that's not futile. That's defiant. That's beautiful. Because the alternative, doing nothing, creating nothing, caring about nothing because it will all end anyway, is a kind of premature heat death. It's choosing entropy now instead of fighting it for as long as we can. And humans, for all our flaws, are fighters. We build knowing that our buildings will crumble. We love knowing that we'll lose. We create knowing that our creations will fade. We do it anyway because the doing is the point. Consider the work of the Long Now Foundation, established in 1996 by computer scientist Danny Hillis and musician Brian Eno. Their mission is to foster long-term thinking by building a clock designed to run for 10,000 years. The Clock of the Long Now, currently under construction inside a mountain in Texas, uses a mechanical computer to keep time, powered by the thermal cycles of day and night. It's designed to tick once per year, chime once per century, and display the correct time for 10 millennia. 10,000 years is nothing on cosmic scales. It's 0.00007% of the time until the last star dies. But it's everything on human scales. 10,000 years ago, humans were just beginning to develop agriculture. Writing didn't exist. Cities didn't exist. Civilization as we know it didn't exist. The Clock of the Long Now is asking, what will humans be like 10,000 years from now? Will we still exist? Will we remember who we were? The clock is not trying to outlast entropy. That's impossible. It's trying to expand our temporal perspective, to make us think beyond our own lifetimes, beyond our own civilizations, beyond the immediate future. It's training us to think on longer timescales, to care about consequences we'll never see, to build things that will outlast us. Not because they'll last forever, nothing lasts forever, but because the attempt to make them last is itself meaningful. Now let's examine the most extreme proposal for preserving consciousness against the heat death, the omega point theory, developed by physicist Frank Tipler in 1994. Tipler argued that if the universe were to collapse in a big crunch, which we now know it won't, the final moments before the singularity could support an infinite amount of computation. As space contracted, energy density would increase, allowing computers to run faster and faster. In the final microseconds before the crunch, an infinite number of thoughts could be thought, an infinite amount of experience could be experienced. Tipler called this the omega point, a moment of infinite consciousness at the end of time. He suggested that advanced civilizations could upload themselves into this final computational substrate, achieving a kind of technological immortality. Not eternal life in the sense of lasting forever, but eternal life in the sense of infinite subjective experience, compressed into finite objective time. The problem, of course, is that the universe isn't collapsing. It's expanding, accelerating, heading toward heat death, not a big crunch. The omega point is impossible in our universe. But the idea reveals something important about human psychology. We desperately want to believe that consciousness can survive, that meaning can persist, that the heat death is not the final word. We want to find loopholes in thermodynamics, escape hatches in the laws of physics, ways to cheat entropy's victory. But there are no loopholes. The second law is not a suggestion. It's not a guideline. It's a fundamental constraint on reality itself, emerging from the statistical nature of matter and energy. You cannot decrease the total entropy of a closed system. You cannot reverse time's arrow. You cannot escape the heat death. These are not technological limitations. They're not problems that better engineering can solve. They're features of the universe itself, as fundamental as the speed of light or the charge of an electron. And yet, and this is crucial, the heat death being inevitable doesn't make it imminent. We have time, vast amounts of time by human standards. The sun will continue to shine for another 5 billion years. The Milky Way will continue to form stars for another trillion years. Even the smallest red dwarfs will burn for 10 trillion years. That's enough time for billions of civilizations to rise and fall. Enough time for intelligence to spread across galaxies, to transform matter and energy in ways we can't imagine, to explore every possible configuration of atoms and ideas. The heat death is coming, but it's not coming soon. And in the time we have, we can do something extraordinary. We can understand. We can map the universe, decode its laws, predict its future. We can be the universe's way of knowing itself before the knowing becomes impossible. That's not a consolation prize. That's the main event. Let me show you what this understanding looks like at the cutting edge of physics. In 2019, the Event Horizon Telescope collaboration released the first direct image of a black hole, the supermassive black hole at the center of the galaxy M87, 55 million light-years away. The image showed a ring of light surrounding a dark shadow, exactly as general relativity predicted. It was a triumph of human ingenuity. 8 radio telescopes scattered across the planet, synchronized to nanosecond precision, combining their data to create an Earth-sized virtual telescope. But here's what makes this achievement philosophically profound. We imaged an object that is, in some sense, the universe's closest approximation to the heat death. A black hole is maximum entropy for its mass. It's the end state of stellar collapse, the final configuration of matter that has given up fighting gravity. Inside the event horizon, time and space swap roles. The singularity at the center is not a place but a moment. The moment when everything that falls in reaches infinite density and zero volume. It's a preview of the heat death, compressed into a single point. And we photographed it. We looked at entropy's victory and said, quote, 23. That's not nihilism. That's curiosity. That's courage. That's consciousness refusing to look away from its own eventual fate. Now let's talk about the one thing that might offer a genuine alternative to the heat death. The possibility that our understanding of physics is incomplete. Because everything I've told you so far is based on our current theories. General relativity, quantum mechanics, thermodynamics. These theories have been tested extensively and have never failed. But they're not complete. We know they're not complete because they contradict each other at extreme scales. General relativity describes gravity as the curvature of spacetime, and it works perfectly at large scales: planets, stars, galaxies. Quantum mechanics describes the behavior of particles and fields, and it works perfectly at small scales: atoms, nuclei, elementary particles. But when you try to combine them, when you try to describe the quantum behavior of spacetime itself, the math breaks down. You get infinities, contradictions, nonsense. This is the problem of quantum gravity, and it's been unsolved for nearly a century. String theory, loop quantum gravity, causal set theory. These are all attempts to reconcile general relativity with quantum mechanics, to find a deeper theory that contains both as special cases. And if such a theory exists, it might change our understanding of the heat death. Not eliminate it. The second law is too fundamental for that. But perhaps modify it in ways we can't currently predict. For example, some versions of string theory suggest that our universe is a 4-dimensional membrane floating in a higher dimensional space. If that's true, then energy might be able to leak out of our universe into the bulk, or leak in from other universes. The heat death might not be the end of our universe, but a transition to a different state, connected to a larger multiverse that continues to evolve. Or consider the holographic principle, which suggests that all the information in a 3-dimensional region of space can be encoded on its 2-dimensional boundary. If the universe is fundamentally holographic, then the heat death might not destroy information, but merely scramble it beyond recovery. And if information is preserved, then in principle, in some unimaginably distant future, it might be possible to reconstruct the past, to recover everything that was lost. These are speculations, not predictions. We have no evidence that string theory is correct, no proof that the holographic principle applies to the entire universe, no reason to believe that quantum gravity will save us from the heat death. But the fact that our current theories are incomplete means we should be humble about our predictions. The heat death is the most likely outcome based on what we know. But what we know is not everything. And that brings me to the final, most important point. The heat death is not a reason for despair. It's a reason for urgency. Because if consciousness is temporary, if the universe's ability to know itself is limited to this brief window of cosmic history, then every moment of awareness is precious. Every thought, every discovery, every act of understanding is a victory against entropy, a defiant assertion that we exist, we matter, we know. The universe is dying, but we are alive. And in the time we have, we can do something that no other physical process can do. We can understand why. We can trace the arc from Big Bang to heat death, from minimum entropy to maximum entropy, from the first moment of time to the last. We can be the universe's way of comprehending its own fate, of staring into the abyss with clear eyes and steady minds, of saying, quote, 24, that's not nothing, that's everything. That's the entire point of being alive in a dying universe. Not to escape the heat death, that's impossible, but to witness it, understand it, and create meaning in defiance of it. To build, love, think, and know, even though it will all end. Especially because it will all end. The heat death is coming. The long thermodynamic silence awaits. But it is not here yet. And until it arrives, we have work to do. We have stars to study, equations to solve, universes to understand. We have each other, and we have this moment, and we have the astonishing privilege of being the universe's way of knowing itself before the knowing becomes impossible. That is not a tragedy. That is a gift, and we should use it while we can. But now we need to ask the question that physics cannot answer. The question that sits beneath all the equations, all the measurements, all the predictions about black holes and proton decay, and the long thermodynamic silence. The question that makes the heat death not just a scientific fact, but a philosophical crisis. Why does the universe exist at all if it's destined to end in maximum entropy? Think about it. The Big Bang created a universe in an incredibly low entropy state. Hot, dense, uniform, but with tiny quantum fluctuations that would eventually become galaxies and stars and you. That initial state was extraordinarily improbable. If you randomly arranged all the matter and energy in the universe, the chances of getting the specific low-entropy configuration of the Big Bang are roughly 1 in 10 to the power of 10 to the power of 120. That's not just unlikely. That's a number so small, it makes the probability of winning every lottery on Earth simultaneously look like a certainty. And yet, it happened. The universe began in that improbable state, and it's been sliding toward probable, high-entropy states ever since. Why? What set up those initial conditions? What wound the cosmic clock that's now running down? Physics can describe how the universe evolves from low entropy to high entropy, but it cannot explain why there was low entropy to begin with. That's not a gap in our knowledge that better observations will fill. It's a boundary where physics ends and philosophy begins. In 1998, physicist Sean Carroll at Caltech began exploring this question seriously. He pointed out that the low-entropy beginning of the universe is the most profound mystery in cosmology, more mysterious than dark matter, more puzzling than dark energy, more fundamental than the nature of time itself. Because if the universe naturally tends toward high entropy, then starting in a low-entropy state is like finding a shattered glass spontaneously reassemble itself. It's not impossible, according to the laws of physics, but it's so improbable that it demands explanation. Carroll proposed several possibilities. Maybe our universe is part of an eternal multiverse where different regions have different entropy levels, and we happen to exist in a low-entropy pocket because only such pockets can support observers. Maybe the Big Bang wasn't the beginning, but a transition from a previous state, and the low entropy was inherited from whatever came before. Maybe there's a deeper law of physics we haven't discovered yet that explains why universes begin with low entropy. But here's what's remarkable. None of these explanations eliminate the mystery. They just push it back one level. If our universe is part of a multiverse, why does the multiverse exist? If the Big Bang inherited low entropy from a previous state, where did that state come from? If there's a deeper law, why does that law exist rather than some other law? At some point, you hit bedrock. a brute fact about reality that has no further explanation. And that brute fact is, the universe exists. It started with low entropy, and it's evolving toward high entropy. Why? We don't know. We may never know. This is what philosophers call the cosmological mystery, and it's intimately connected to the heat death. Because if the universe is destined to reach maximum entropy and stay there forever, then the entire history of stars and galaxies and life is just a brief fluctuation, a temporary deviation from equilibrium that will eventually be erased. The universe will spend infinitely more time in the heat death state than in any other state. So in some sense, the heat death is the universe's natural condition, and everything else, including us, is the anomaly. Now let's examine what we don't know about the heat death itself, because the gaps in our understanding are as important as what we do know. We know that entropy increases. We know that the universe is expanding and accelerating. We know that stars will die and black holes will evaporate. But there are crucial questions we cannot answer with current physics. First, what is dark energy really? We know it exists because we've measured its effects, the acceleration of cosmic expansion. We know it comprises roughly 68% of the universe's total energy. But we don't know what it is. The simplest explanation is that it's the cosmological constant, a property of space itself that causes space to expand. But the measured value of the cosmological constant is roughly 10 to the power of 120 times smaller than quantum field theory predicts it should be. This is called the cosmological constant problem, and it's one of the worst predictions in the history of physics. If dark energy is not a constant, but a field that changes over time, something called quintessence, then the fate of the universe might be different than we predict. The expansion might accelerate faster, leading to a big rip where space itself tears apart. Or it might slow down, allowing gravity to eventually halt the expansion and trigger a big crunch. Or it might do something we haven't imagined yet. We simply don't know. Second, do protons actually decay? We've never observed proton decay, despite decades of experiments. The current lower limit on proton lifetime is 10 to the power of 34 years. But that's just a limit. It doesn't tell us whether protons decay at all. If protons are absolutely stable, then matter persists forever, even after all the stars have died and all the black holes have evaporated. The universe would be filled with cold, dark lumps of iron and other stable nuclei floating in the void for eternity. That's a different kind of heat death than the one where protons decay and matter dissolves into radiation. Third, what happens to information at maximum entropy? Quantum mechanics says information is conserved. It cannot be created or destroyed, only transformed. But at maximum entropy, information is maximally scrambled, spread across the entire universe in subtle quantum correlations that are impossible to decode. Is that information truly lost? Or is it merely hidden? If you waited long enough, far longer than the Poincaré recurrence time, could quantum fluctuations spontaneously reassemble that information into something meaningful? We don't know. Fourth, is consciousness purely physical, or is there something more? Every experiment suggests that consciousness is what brains do, that subjective experience emerges from the physical processes of neurons firing and synapses connecting. But we still don't have a complete theory of consciousness. We don't know why there's something it's like to be you, why there's an inner life, a first-person perspective, a sense of what it feels like to see red, or taste coffee, or feel pain. If consciousness is purely physical, then it ends when the heat death makes complex information processing impossible. But if there's something non-physical about consciousness, some aspect that doesn't reduce to particle interactions, then maybe, just maybe, consciousness could persist in forms we can't currently imagine. These are not idle speculations. These are genuine gaps in our understanding, places where our best theories give ambiguous or incomplete answers. And they matter because they affect what the heat death actually means. Is it the absolute end of everything? Or is it a transition to something else? Is it the final state? or just the longest-lasting state before something new emerges? We don't know. And that uncertainty is important to acknowledge. But here's what we do know, and it's enough to change how you see everything. The universe is not eternal. It had a beginning, and it will have an end, or at least a transformation into a state so different from the current universe that end is the appropriate word. The stars will die, the galaxies will fade, the black holes will evaporate, and eventually, the universe will reach a state where nothing happens, nothing changes, and nothing ever will again. That's not speculation, that's physics. And yet, right now, in this moment, you are here. You are conscious. You are aware. You are part of the universe that is temporarily complex enough to understand itself. You are made of atoms, forged in the cores of dying stars, arranged in patterns intricate enough to think and feel and know. You are a local decrease in entropy, a temporary rebellion against the second law, a brief flash of order in a universe sliding toward disorder. Let me bring this back to where we started, your coffee getting cold. That cooling coffee is not just a mundane fact about thermodynamics. It's a microcosm of the entire universe's fate. The heat flows from the hot coffee to the cool air, increasing entropy, moving toward equilibrium. Eventually, the coffee reaches room temperature and stops changing. That's the coffee's heat death, the moment when it reaches maximum entropy relative to its environment, and nothing more can happen. But here's what makes this profound. While the coffee was hot, you could drink it. You could extract energy from the temperature difference between the coffee and your body. You could use that energy to power your neurons, to think thoughts, to have experiences. The coffee's journey from hot to cold was not just a loss of order, it was an opportunity for process, for change, for life. And when the coffee reached equilibrium, that opportunity ended. The universe is the same. Right now, it's far from equilibrium. There are hot stars and cold space, dense galaxies and empty voids, energy gradients everywhere. And those gradients make everything possible. Fusion in stellar cores, chemistry on planetary surfaces, metabolism in living cells, computation in brains. All of it powered by the flow of energy from hot to cold, from order to disorder, from low entropy to high entropy. When the universe reaches maximum entropy, those gradients will be gone. No more hot and cold, just uniform temperature everywhere. No more dense and sparse, just uniform density everywhere. No more energy flow, no more processes, no more change. The universe will be like your coffee after it's cooled, still existing, still containing the same atoms and energy, but no longer capable of doing anything interesting. No longer capable of supporting life, or thought, or awareness. And that's why this moment matters. Not despite the heat death, but because of it. Because the window of complexity is finite. Because consciousness is temporary. Because the universe's ability to know itself is limited to this brief era when stars shine and gradients exist and entropy hasn't yet won completely. We are living in the universe's youth, the only time when understanding is possible. Now, let me take you back to the very beginning of this journey. Remember how we started? With your coffee getting cold, your ice melting, your phone battery draining. With the observation that entropy is not some distant abstraction, but a present reality, operating right now, in this moment, in everything you do. We've traveled from that simple observation to the death of the last star, the evaporation of the last black hole, the decay of the last proton, the long thermodynamic silence that awaits at the end of time. But here's what I want you to understand. That journey, from cooling coffee to cosmic heat death, is not a journey from meaning to meaninglessness. It's a journey from ignorance to understanding. Because now you know. You know why your coffee cools. You know why stars die. You know why the universe is expanding and accelerating and heading toward a state where nothing will ever happen again. You know the deepest truth about physical reality, that entropy always increases, that time has a direction, that everything is temporary. And in that knowledge, there is something extraordinary. Not comfort exactly, not hope in any conventional sense, but a kind of cosmic perspective that makes your brief existence more precious, not less. You are not separate from the universe. You are part of it. You are the universe's way of experiencing itself, of understanding itself, of knowing that it exists before the knowing becomes impossible. You are made of star stuff, as Carl Sagan said. But you're more than that. You are star stuff that has become conscious, that has learned to ask questions, that has figured out the laws of thermodynamics and traced them to their ultimate conclusion. That is not nothing. That is everything. That is the entire point of being alive in a dying universe. Not to escape the heat death, that's impossible. Not to prevent it, that's forbidden by the laws of physics. But to witness it, to understand it, to create meaning in defiance of it, to build civilizations and write symphonies and solve equations and love each other, even though entropy will eventually erase it all. Especially because entropy will eventually erase it all. Because here's the final truth, the one that makes the heat death bearable. Meaning is not something the universe gives us. It's something we create, here and now, in the brief window when creation is possible. Every act of love is meaningful because it's temporary. Every moment of beauty is precious because it will fade. Every discovery is valuable because it will be forgotten. The heat death doesn't make these things meaningless. It makes them urgent. It makes them matter. You are a pattern of low entropy in a universe sliding toward disorder. You are a temporary island of complexity in an ocean of simplicity. You are a brief flash of consciousness in an eternity of darkness. And that's not a tragedy. That's a miracle. Because against all odds, against the inexorable pull of entropy, against the second law of thermodynamics itself, you exist. You are here. You are aware. You are alive. The universe is dying. The stars will fade. The galaxies will disappear beyond the cosmic horizon. The black holes will evaporate. The protons will decay. And eventually, nothing will remain but photons and leptons separated by distances measured in light centuries, all at the same temperature, all moving away from each other as space continues to expand forever. The long thermodynamic silence will descend, and it will never end. But that silence has not descended yet. Right now, in this moment, the universe is awake. It is aware. It is alive. And you are part of that awakening. You are the universe's way of knowing itself before the knowing becomes impossible. You are consciousness emerging from matter, order arising from chaos, meaning created from meaninglessness. So what do you do with that knowledge? What do you do when you understand that everything is temporary, that entropy always wins, that the heat death is inevitable? You do what humans have always done. You create anyway. You love anyway. You build anyway. You think and feel and experience anyway. Not because it will last forever, nothing lasts forever, but because the doing is the point. Because consciousness, however brief, is valuable. Because awareness, however temporary, is precious. Because you are here, now, in this moment, and that is enough. The heat death is coming, but it is not here yet. And in the time we have, whether that's decades or centuries or billions of years, we can do something extraordinary. We can understand. We can know. We can be the universe's way of comprehending its own fate, of staring into the abyss with clear eyes and steady minds, of saying, I see you, entropy. I know what you're going to do, and I'm going to fight you anyway, for as long as I can, because that's what consciousness does. Your coffee is getting cold. The ice in your drink is melting. Your phone battery is draining. And in this exact moment, you are witnessing the same force that will one day kill every star, extinguish every galaxy, and reduce the entire universe to an ocean of darkness so complete that nothing will ever happen again. But you are also witnessing something else. The universe's brief, brilliant flash of self-awareness. The moment when matter became complex enough to understand entropy. The instant when consciousness emerged and looked at the dying universe and said, quote 27, "That is not futile. That is not nihilistic. That is the most defiant, courageous, beautiful thing that consciousness can do. To exist in a dying universe and choose to matter anyway. To build and love and think and know, even though it will all end. To be the universe's way of saying, not yet, to the heat death, for as long as we possibly can. The long thermodynamic silence is waiting, but it is not here yet. And until it arrives, we have work to do. We have stars to study, equations to solve, universes to understand. We have each other, and we have this moment, and we have the astonishing privilege of being alive in a universe that is still complex enough to support consciousness. So, drink your coffee while it's hot. Watch the ice melt. Feel your phone battery drain. And know that you are witnessing entropy in action, the same entropy that will eventually claim everything. But also know that you are more than a witness. You are a participant. You are consciousness itself, briefly emerging from the void, understanding the void, creating meaning in defiance of the void. The universe is dying, but you are alive, and that makes all the difference.